So first of all, we're going to start by trying to find this limit as x goes to 2 of x squared plus 2x minus 8 over the quantity x minus 2. So if you're like me, you're a little bit lazy and you say, hey, I know that I'm going to have a problem if the denominator is 0. So rather than start putting numbers into the numerator, let's go ahead and plug it in the denominator and see what we get. And we end up with a 0 in the denominator. So we know that the limit is not possible to be found when x is 2 in the way that this is currently written. Okay, so what do you suggest we do? Let's try and simplify first. So if we're wanting to simplify, we have a trinomial in the numerator, right? What can we do to that? We could factor it. So if we try to factor the numerator, it's like finding the limit as x goes to 2 of x and x. Factors of 8 that subtract to become 2 are 4 and 2, right? And we want the larger one to be positive. And lo and behold, it matches what is in the denominator, doesn't it? So we cancel these. And now what is the limit as x goes to 2? X plus 4, we sub in 2. 2 plus 4, we get 6. And that's our answer. So let's look at what this looks like in graphical form. When we take that trinomial and we divide it by, so quadratic, we divide it by a linear function, because they cancel, it ends up being a line. But at that particular spot, as x is approaching 2, the y is approaching 6, but it can't be 6. Make sense? So on the left-hand side is approaching 6. On the right-hand side is also approaching 6. So when a function approaches the same number from both the left and the right, the limit does exist, right? And that limit happens to be 6. Make sense? All right. So next example. How are we going to find the limit as x goes to 2 of the quantity x minus 2 over the quantity x cubed minus 2x squared plus 2x minus 4? We know we have a problem if the denominator becomes a 0, right? So let's do a quick synthetic division test to see what's happening here. If I synthetically divide and see what my remainder becomes, I'm going to divide 1, negative 2, 2, negative 4 by a positive 2. I drop my 1. 1 times 2 is 2. Adding, I get 0. 2 times 0 is 0. Adding, I get 2. 2 times 2 is 4. Adding, I get no remainder. So when I plug that in, I will get a 0 in the denominator. So we have to do something about that. Factor by grouping. Okay, so let's group our first two together. What do these guys have in common? Because the greatest common factor is an x squared. So what's left? Good. Okay, if I group these two together, what do they have in common? A positive 2, so if we divide that out, each term by 2, we get, that's nice, that's convenient. Okay, so we're going to have the limit as x goes to 2 of x minus 2 over, what did the first 2 have, or what do we put in the first parentheses? X squared plus 2 and the common term x minus 2. And because now we have factors, a factor in the numerator and the factor in the denominator can both be canceled. And what will our limit be? 1 over x squared plus 2. And now when we evaluate that limit at x equals 2, we get 1/6. Okay, this is what it looks like. Thank you. So there's our original function. And at 2, it did not exist. But as we approach 2 from the left, y is approaching 1/6. As we approach 2 for x from the right, y is also approaching 1/6. So our limit is 1/6. Function didn't exist there, but the limit does. So far, so good? Okay, questions on this one? Okay, next example. Now we want to find the limit as x goes to 1 of x minus 1 over x cubed minus 1. And a quick check shows us that we get a 0 in the denominator. So now we need to factor. All the factoring, you probably had the least amount of practice on the difference of sums of cubes, right? So let's remember what that pattern was. If we have a cubed minus b cubed, it factored into a binomial and a trinomial. So if you remember what others have used, the SOAP idea that tells you the signs, same, opposite, and then always positive. So because this is negative, we're going to have the same sign, the opposite sign, and then always positive. So we strip off our cubes. The cube root of a cubed is a, cube root of b cubed is b, and then we square the first, a squared, multiply them together, ab, and square the last. So how will x cubed minus 1 factor? Okay, always positive for the last. So now we've got the limit as x goes to 1 of x minus 1 over that. And now that they're factors, we can cancel. We can't cancel sums or differences, but we can cancel factors or products. Okay? So when we do that, we have simply the limit as x goes to 1 of 1 over x squared plus x plus 1. And what will our result be? 1 over 3. 1 squared is 1, plus 1 is 1, plus 1 more, so 3. Make sense? All right, so that's why we had that review of factoring. So we're going to be doing some factoring this chapter. All right, next example. So first of all, here's what this one looked like. And we can see that it's undefined when x is 1. But from the left, we peek out and then we approach 1/3. From the right, we're raising and we're increasing to 1/3. So 1/3 is our limit. Okay. All right. So what are we going to do about this? The limit as x goes to 0 of the quantity x plus 9 into the square root of the quantity x plus 9 minus 3 all over x. Unless we have factors we can't cancel, right? So what can we try here? Let's try to square it, okay? Squaring it kind of makes sense. It might seem like it would help. But in order to square something, it's done with an equation, not an expression, because you have to be able to square both sides of the equation. Okay, so when we're working with factors or fractions, we have to either do the same thing to the numerator and the denominator, So we're multiplying by 1, or we have to be able to do the same thing to both sides of the equal sign. And we don't have another side of the equal sign, so we can't just square. Okay, but I like where you're going with that, because what would happen if what are we trying to do? Maybe eliminate the square root, right? Okay, so that's why you're thinking squaring. So what's another way that we can eliminate the square root? What could we multiply it by? The square root of x plus 9, right? But if we do that, then we're going to introduce it here. If we just distribute it through to both, right? So what do we need over here? A plus 3, because now we have the difference of squares, don't we, in factored form. But because this is an expression, we can't do it to the other side, so we have to multiply this numerator and denominator by exactly the same thing. So now we've multiplied by effectively 1, which doesn't change the actual expression other than its appearance, right? All right, so when we do that, what will we get in the numerator? Boiling this out first times first will get us x plus 9. Outsides is going to get us a positive 3 times the square root of x plus 9, but insides is going to get us a negative 3 times the square root of x plus 9. They're supposed to cancel, right? That's why we did this by design. And finally, last times last, minus 9. I kind of like that. And down here, let's leave this in factored form. We're taking x times this square root of x plus 9 plus 3. Now what? We could distribute it in, but we could cause more problems, because our goal is to eventually try to get rid of this x in the denominator, right? What's in the numerator right now? Just an x, right? Because plus 9 minus 9 is gone. So this is the same thing as the limit as x goes to 0 of x over x times the square root of x plus 9 plus 3 in parentheses. That's good, right? Because now we've eliminated our x's, and we just have a 1 up here. Can we evaluate the limit now? Yeah. The limit as x goes to 0 of 1 over the square root of 0 plus 9 plus 3 is going to be 1 over 6 again. Not very unique answer. We've had that a couple times now, but 1/6 is our limit. Shall we see what it looks like in graphical form? Kind of looks linear, doesn't it? At least at this zoomed in at this range. And that makes sense. As we approach from the left, we approach x is 0 from the left, y is about a 1/6. This is negative 1. This would have been positive 0.5, 5/10, and same thing's happening from the right. Make sense? All right. So you'll hit a stage in your book or a few problems in your book that say approximate the limit. And they want to make sure that you know how to run your graphing calculator. Okay? So do you need to see that done again today? How to use the table, how to plug these into the y equals, or are we okay? Okay. So we can look at this and say, wait a minute, x is going to a negative 1, that's going to cause us a problem, right? But we could factor this one, couldn't we? X minus 5, x plus 1 would do the trick, and we could work it out. Okay? But what they want you to see is what happens in the calculator mode. So you would plug in your y1 the quantity x squared minus 4x minus 5. Make sure it's in parentheses, so that whole numerator is being divided by the quantity x plus 1. And then when you do that, you graph it, and you're going to see that as we're approaching a -1, we're going to have a hole, we're going to have a problem. But we can zoom in on it, or we can go to our table and figure out what that number is. So we would plug in a -1.003 maybe, and let our change in table be 0.001, so we can get really, really close to it without actually touching it, or if we do touch it, we end up getting an error, right? At -1, we'd have an error. But we would find out that we were at -6.001, really close to the left side of it, and a -5.999, really close to the right side of it, just like we did the other day. So we know that it's approaching -6. Make sense? Okay. That's really useful with a problem like this one. Because if we look at the limit as x goes to 0 of the tangent of x over x, we say, okay, x in the denominator is a 0, that would cause a problem. But is there something that we can do to the tangent that's going to make that x in the denominator cancel out somehow? The tangent's the sine over the cosine, right? 1 over the cotangent. If we would take it times the tangent, we would get tangent squared, because we can't just square both sides, right? We don't have an equal sign. So even if we did a tangent squared over tangent times x, multiplying both the top and the bottom by the same, now we could get to 1 tangent squared plus 1 equals secant squared, so secant squared minus 1, still not going to cancel with x, is it? So we think about all of our identities that we have for tangent, and nothing's going to happen. So this is where we need to break out the calculator and see what's going to happen with it. Okay. Do you want to go through the steps of that? Or are you comfortable with it? See the steps? Okay, let's do that. So let's break out the calculators. All right, so we'll clear out whatever we had in our calculator before. And we want to, in the numerator, put the tangent of x. Now, is it going to matter if x is in radians or degrees? Not, is it? Okay, so we're going to take the tangent of x, and we're going to divide it by x. Okay, so when we hit graph, it's going to look a little crazy, right? And we want to set up our table so that we can get really close to 0 and see what happens to tangent at that point. Okay, so if we plug it in really close to 0, we're going to set up our table. Table setup is the second of window. And we're going to say, let's make the table be starting at 0.001, maybe. So we're really close to 0, but not quite there. And we want our change in table, our delta table, to be 0.001, maybe. So it's going to change by the thousands every step. And now if we go to our table menu, second of graph, we get 0.001, we're at 1, 0.002, we're at 1, 0.003, we're at 1. We're seeing a consistent 1 here, aren't we? Watch what happens when we go up. At 0, we have an error. We can't divide by 0. And at -0.001, 2, and 3, we're also at 1. Then we need to see those steps again. Went through them kind of quickly. All right, so what is our answer? 1. Okay, for our limit. The limit of as x goes to 0 of the tangent of x over x is 1. And we could tell that by zooming as well. If we had our graph in here and we did a zoom, we can say, hey, I want to make a box around what I'm trying to zoom in on. I kind of want to see what's going on over here at 0. And so I arrow to some place close to 0. I press enter, and I go down and right or up and left, depending on where I was on my screen. And I press enter again. And now you can see a little bit more of what the detail is of that, what it was doing when x was 0. Make sense? And you can use your trace function to move. I'm tracing, and when I'm here, I'm at 1, 1. As I get further away, though, it's going to start to climb. Okay? That's what you're doing today. Okay? So this is what it looked like in Desmos, zoomed out, right? But as we approach x is 0 from the left, we're at y, 1 for y. And as we approach x is 0 from the right, we're also at 1 for y. Function's not defined at x is 0, but the limit is. And it's 1. All right, there's your assignment.